Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to find the volume of a solid generated by revolving a region bounded by four equations. So those equations are, in fact, we're going to, by the way, revolve the region about the line x equals 5. And what is this region? Well, the region is obtained by x, y equals 3, y equals 1 horizontal line, y equals 4 another horizontal line, and x equals 5 vertical line. So the very first thing to check here is what the region looks like. Let me just show you from my end what I got here. You will see the details of that within the video. I just want to give you some heads up. So this is in fact the region, green region, bounded by four of these equations, and we're going to revolve that around x equals 5 vertical line. Okay, so let's see what kind of revolution we have, what kind of three-dimensional object we have after the revolution. So this is in fact a wedge type three-dimensional object, as you see, and we're going to find the volume of this three-dimensional shape. Okay, so and the axis of revolution here is vertical. So let me just remind you the disk method where the axis of revolution is vertical. All right, here's a table that represents the volume of a solid of revolution by the disk method. We have two different formulas here, two different columns. One is the horizontal axis of revolution. The other one is the vertical axis of revolution. As I said, we're interested in the vertical axis of revolution. So that means that we're going to take a slice from that region perp to the vertical axis of revolution. So as you see, I got this piece here that comes with thickness dy. And now after you revolve this around, let's see what it looks like. All right, after the revolution, that's the disk that we have. And since the thickness is chosen to be dy, and since we're using the disk method, so the corresponding radius of the disk is going to be written in terms of y. That's the crucial part, because in other cases, you may have the thickness to be dx, and you have to write the radius in terms of x. But in this particular case, we're going to write everything in terms of y. And the volume of the representative disk is the area of the circle times the thickness. So pi times capital R squared times dy is the volume of the representative disk. But if you sort of like integrate it from C to D, as you see, so that you can actually find the volume of the three-dimensional object obtained by revolving the region about the vertical axis. Okay, so I think that was a long start, so I'm going to stop here because you're going to see most of the details in the video better explained. So why don't we hit the road? All right, let's take care of this question. So we're going to find the volume of the solid generated by revolving the region bounded by the graphs. In fact, there are four of them. One is xy equals 3. The other one is y equals 1, which is a horizontal line. And y equals 4 is another horizontal line. And x equals 5 is a vertical line. So, and we're going to revolve the whole region about the line x equals 5. Well, at this moment, why don't you go ahead and so like try to graph each function in the same plot to see what the region looks like. And the way you graph this function is you can implicitly graph this function, or you can look at y equals 3 over x if you want to. And as I said, y equals 1 and y equals 4 are horizontal lines, and x equals 5 is the vertical line. All right, so please do it, and if you want, you can hand sketch it as well. So let me just show you what I got from my end. Okay, so the blue graph is xy equals 3, and purple one is y equals 4, and red one is y equals 1. And this black vertical line is, in fact, x equals 5. Okay? So my region is bounded by four of these curves. On the left, xy equals 3. In the bottom, y equals 1. On the right, x equals 5 vertical line. And at the top, y equals 4 horizontal line. Okay. So this is the first part of the problem, to be able to find this green region bounded by these four graphs, okay? All right, what I'm going to do is I'm going to revolve this region around x equals 5 vertical line. So the revolution, the axis of revolution is vertical, okay? And we're going to use the disk method to start with. And in the disk method, you get slices vertical to the axis of revolution. So let me just show you my representative slices here. So we get like, as I said, slices vertical to the axis of revolution. And we keep revolving those around the x equals y vertical line. And you're going to get like disks, obviously, with thickness dx. And you can do it for every slice that you pick within the region. Okay? Now let me just show you how the three-dimensional object looks like, because if I keep doing that all the way, right? And you're going to get like this kind of like three-dimensional object. Okay? A vase type three-dimensional object. The bottom is flat, the top is flat, right? So here we go. This is the region referred in the statement of the question, and that's what we found, right? So now we're going to revolve this around x equals 5 vertical line, which is in fact this line here, right? Here we go. So let's see what we're going to have. Okay, okay, okay. All right, this is exactly what you got at the end, okay? So now the question is, how are we going to find the volume of this three-dimensional object, okay? So let me just clean this a little bit, and so that we have some space. Since we chose the slices vertical to the axis of the revolution, we're not going to have any dx anymore, but we are going to have dy, okay? And the height of each slice that you come up with is going to be written in terms of y, okay? So for that reason, maybe I should consider this equation xy equals 3 as x equals 3 over y, okay? So let's see what we have. Let's say like this slice, my representative slice here, okay, is y units far from the origin, okay? So I need to find this distance here, which is going to tell me exactly what the height is, okay? So let me call this to be r, because that's going to be the radius of the disk after the revolution, okay? All right, let's try to find r. The first thing to do is that if this slice is y units far from the origin, then the corresponding x coordinates here, when you're on this point here, is going to be determined by this equation here, right? X equals 3 over y. So that distance is, in fact, 3 over y. Okay? And we also know that the distance from here to here is fixed, and that's 5 units. Okay? So in other words, this part of the disk, the bottom part of the disk, is always touching x equals 5 line, and that doesn't change whenever you change one slice to another. See, I still have the bottom portion touching the x equals 5 line, but the upper part of that touches the blue curve, and it depends on that in fact the height here is determined by where at what y you're at. Okay, so so therefore r is going to be found by 3 over y, 5 minus 3 over y, right? 5 is the bigger one. 5 minus 3 over y is in fact what r of the disk is. All right. So now we can go ahead and write down the volume formula. Okay, so the volume is going to be pi r squared dy, because we have dy, right? Now let's check what the limits are. So all the y's within the region are ranging from 1 to 4, right? 1 to 4. So that means y equals 1 and y equals 4. All the y's within the region are varying from 1 to 4. So the limits would be 1 to 4. And let's just put capital R back into the formula. That is 5 minus 3 over y squared, quantity squared dy. Okay. So up to this point, it was all the geometry and coming up with the right R and the limits and everything, and the use of the disk method appropriately. But from this moment on, it's just the evaluation of a definite integral. So for that reason, we're going to expand the whole integrand out. So that's 25 minus 30 over y plus 9 over y squared dy. And this is sort of like integrable in one shot, so let's just integrate that. So 25y minus 30 divided by y. Well, 30 times 1 over y, you can take it that way. And that's a very special integral that is ln y, right? And as well, 9 over y squared can be written as 9 times y to the minus 2. And if you apply the power rule for integration, so it's going to be 9 times y to the minus 1 divided by minus 1. So that's in fact minus 9 over y. And here lower limit is 1, upper limit is 4. Okay. So let me just continue with a different color. I'm going to plug in 4 for y by using the fundamental theorem of calculus, right? Pi 100 30 ln 4 minus 9. Okay. Minus pi, we're going to plug in the lower limit, 25 ln 1 and 9. Okay. And ln 1 is 0 already. And collect all the like terms and simplify this and get the exact form. So you should get 327 pi over 4 minus 30 pi ln 4. Okay. And that is the exact value. And if you want to find the approximate value, that should be like 126.17. Okay. And here the three-dimensional object here that we got has the volume to be approximately equal to 126.17. Okay. Here we use the disk method, and one observation was that if you find a slice, if you want to choose a slice within the region, you have to choose the one perp to the axis of rotation, and here the axis of revolution is the vertical line vertical line x equals 5. Okay, so and we use the disk method to be able to come up with the volume integration formula here. Okay. All right, so this takes care of everything being asked in the question. So thanks for watching. And if you have any questions, comments, or suggestions, please send those to my way. All right, bye.